Good afternoon, students. How is everyone doing? Are we live? You can hear me. If the video is fine, just let me know. All right. Everything seems fine, I think. Right? Okay. Let's start. So without wasting any further time, we will start with some more pre-RMO questions and then we'll move on to IOQM questions since 2021. Right? Good afternoon. Good afternoon. Yes, so we have 2023, we even have 2024 questions. So yes, this includes all PYQs, but not all of them. But yes, PYQs from all the years. I have handpicked the questions that I feel will be really helpful for you. So let's start. Okay. Try this one. There's a set. So just to let you know, guys, the questions that I have selected for today are not going to be as easy as the previous sessions. This is the last session that we are having in this series, which means we have to finish it with a bang, right? We are going to solve some very tricky, some very difficult questions to say the least. So keep your minds open, just think from every angle, and once you're done with the question, once you're done with the solution, and write your answer in the comments or in the chat section. Okay, so we have a set 5, 6, 7, 8, 9 for any partition A, B of E. That means we are partitioning this set maybe like this or like this or maybe 5, 6, 9 and 7, 8. So like this we can partition our set into two sets such that A and B are non-empty. Now consider the number obtained by adding the product of all elements of A to the product of all elements of B. We're taking A and B and we're multiplying the numbers in A, we're multiplying the numbers in B, and we're adding the two products. Let n be the largest prime number among these numbers. Find the sum of digits of n. 17. Yes, 17 is the correct answer. Good job. Let's see how. So, what do we want? Largest prime, right? So, let's say A has elements A1, A2, A3 or A4. It can be either 4 elements or 3 elements. See, first of all, what do we have to understand? We have to understand that it doesn't matter which numbers go to A and which numbers go to B, as long as there's a partition, because the order doesn't matter here, right? So let's say A has more elements than B. They cannot have equal number of elements because there are 5 in total. Now what are the options? Either A has 4 elements and B has 1 element, or A has 3 elements, B has 2 elements. That is the only possible partition that we can have, such that both are non-empty, right? Now assuming that A has more, right? Because it doesn't matter which one we are taking first. Even if B had more, it didn't matter, right? We need the largest prime number. It doesn't matter how many ways we can partition this. Now, an important thing here is we need a prime number, right? That means if 6 and 8 are in different sets, right? Let's say A has A1, A2, A3, A4 and B has 1, so the product will be B1. And in this case, the product will be A1, A2, A3 plus B1, B2, right? Now, if 6 and 8 are in different partitions, that means 6 will be here, 8 will be here, or 8 is here, 6 is here. But in that case, we can take 2 common out of both of these products and the resulting number will be an even number. Even in this case, if 6 and 8 are in different partitions, then we can take 2 common out of those, and that is why the resulting number will not be a prime number. Now similarly 6 and 9, if they are in different partitions, we can take 3 common out of those. So again it won't be a prime number, which means 6, 8 and 9, all 3 of them have to be in the same partition, because 6 has to be in the same partition as 8 and 6 has to be in the same partition as 9. So we know, and it cannot be in B because B has less number of elements. So we know 6, 8, 9 are fixed here. Now here it's 5 and 7. Here we have 2 options, either 5 or 7, and likewise B1 will be 7 or 5. Now we need the largest numbers, right? So we will start checking in the descending order. What is the largest product, the largest prime possible, right? So the largest will be not when we are just multiplying these 3 numbers. If we are multiplying 6 into 8 into 9, then it will give a smaller number as compared to when we further multiply it with 5 or 7, right? So this will give the larger number. So the largest will be 6 into 8 into 9 into 7 plus 5. What is this value? I'm going to use a calculator because otherwise the entire session will take a lot of time. But if you have calculated, so this comes out to be 3029. Now we check if it's a prime number. You start checking, it's not divisible by 2, it's not divisible by 3, it's not divisible by 5, it's not divisible by 7, but 11, no, not even 11, 13, if we divide it by 13, what do we get? 2, 42, that is 3, 39, 3. So this is not a prime number. We move on to the next one, 6 into 8 into 9 into 5 plus 7, and this is 2167. This is clearly divisible by 11 because 7 plus 1 8, 6 plus 2 8. So this is divisible by 11. I don't even need to check what will be the quotient, what will we get when we divide it by 11, because we can clearly see that it's divisible by 11. So these two are not possible. The only possibility we have remaining is this one, which is 6 into 8 into 9 plus 5 into 7, which comes out to be 432 plus 35, 467. And now you can check that it is a prime number. So the sum of digits of n will be 4 plus 6 plus 7, that is 17. Okay. Now, how many 4-digit numbers A, B, C, D are there such that A is less than B, less than C, less than D, and B minus A is less than C minus B is less than D minus C? So how many such 4-digit numbers can we have? If you're not here to study, please do not disturb the students who are sincerely studying, because we are preparing for the Olympiad. We do not have much time left. So if you're not here to study, you can leave this session, bache, that's totally okay. But I would request that the chat remains clean and the students can actually answer, and I can see the answers here. Okay. 21. Is the answer 21? No, the answer is not 21. So the answer is 7. Let's see how. See, first of all, we have a number A, B, C, D. These are our 4 digits. Now, they are in increasing order, strictly increasing, no repetition allowed, right? And what can be the smallest number? The smallest digit is 0, but because it's a 4-digit number, A cannot be 0. So, A can start from 1 and it can go till 6, right? And the minimum value of A is 1, maximum value of D is 9, right? Now, we are checking the difference between the digits. We know they are increasing. Let this difference be X, this difference be Y, this difference be Z, right? So, X is less than Y, less than Z. And if we add these differences, basically if we add these differences, A plus X plus Y plus Z, we get D, which means X plus Y plus Z is D minus A. And the maximum value of D minus A is 9 minus 1, 8. So, this has to be less than equal to 8. And minimum value of the difference will be when it's 1, 2 and 3, because X has to be less than Y less than Z. So, minimum value will be 6. So, it has to be between 6 and 8, which means X plus Y plus Z can be 6, in which case this is 1, 2, 3. X plus Y plus Z can be 7. In that case, it will be 1, 2 and 4. No other possibility is there, because it has to be in an increasing order. X plus Y plus Z is 8. What are the possibilities here? Either it can be 1, 2, 5 or 1, 3, 4. And these are the possibilities for the difference, right? Now, let's check each case one by one. For 1, 2, 3. D minus A is 6, right? Which means D is A plus 6. Now, D has to be less than equal to 9, which means A has to be less than equal to 3. So, it can be 1, 2 or 3. In total, we get 3 possibilities for A, and accordingly, we will have B, C and D. Once we fix A, we get B, C, D. Similarly, we will do for the others. 1, 2, 4, D is equal to A plus 7, which is less than equal to 9. So, A is less than equal to 2. So, 2 possibilities. Then, for both 1, 3, 4 and 1, 2, 5, D is equal to A plus 8. So, A has to be 1. So, we get 1 for this, 1 for this. So, 3 plus 2, 5 plus 1, 6 plus 1, 7. So, 7 possibilities are there. So, like this, you can calculate for even a larger number, but this will make sure that you do not miss any case. Alright. Now, IOQM problem. This one is, I think, relatively easy. What do you think? 3 couples sit for a photograph in 2 rows of 3 people each. We have row 1 and row 2. Now, what are the conditions? No couple is sitting in the same row next to each other. They can sit away from each other, but no couple is sitting in the row next to each other, and no couple is sitting in the same column. If husband 1 is here, then wife 1 cannot be here. So, like this, we have such possibilities. Now, we have this condition. Now, how many arrangements are possible? think even JEE students should try these questions. These are very good questions. These are some of the questions that you should practice for JEE Advanced. So I think combinatorics is a topic that is, that is something that you can easily solve even if you're preparing for JEE and not for the Olympiad, because the curriculum is quite overlapping. It's mainly logical, and JEE Advanced does tend to have very tricky problems just like the Olympiads. Anyway, but yeah, I think Olympiads are harder. What? 96. 96 is 96 the answer? Yes, 96 is the correct answer. Good job. Let's see how. Now, let's say the couples are H1, W1, H2, W2, H3, W3. Right? Let's say the couples are one wife, one husband, one wife, one husband, one wife, one husband. Now, let's take it case by case. Case 1 is all men in same row. That is, let's say it's in row 1. So, all men are in same row. Now, what is the possibility? First, let's arrange these men. We have to first pick the row. So, 2C1 into arrange the men 3 factorial. Now, we have to arrange the women such that woman 1 cannot be here, woman 2 cannot be here, woman 3 cannot be here. Right? So, that is nothing but derangement, which is 2 into 6 into 2. So, 24. Right? Now, case 2. Two men, one woman in one row, and correspondingly there will be 2 women and 1 man in the other one. So first let's select which row will have 2 men. So we selected the row. So let's say it was first row, and now we have to select which woman can be here. Let's say this case has, this woman is from the third couple. Right? So that means this is W3. We'll check if it's W1 or W2 in the other case. Okay? But now, for now, let's say there are 2 men and 1 woman in this row. So we first selected which row, and now we have to select the seat for the woman. Right? It can either be here or here or here. So 3C1. Now we have to arrange the remaining H3, W1, W2. Now it's the same as derangement. H3 cannot be here, W1 cannot be here, W2 cannot be here. Right? So this is again D3 and no, actually we don't even have to do 3C1. We will just do 3 factorial. Why? Because these 3 can be arranged in any way. It's not like H1 and H2 order is fixed, right? So it can be H1, W3, H2, just like before. We have to just arrange these 3 people. So it's 3 factorial, which is the same as that expression. So this again is 24. Right? Am I missing something? Right? Now, what are the cases are there? We have a case where When H1, H2 and let's say W1 are in the same row, right? Let's say we have these three in the same row. In that case, what was the condition? That they cannot sit next to each other. So that means H1 and W1 have to be in the corner. It can either be H1, H2, W1 or the reverse order, right? That is fine. But now we have H3, W3 and W2 remaining for this. Again, these two cannot sit next to each other, so they have to go in the either side, right? It can either be H3, W3 or W3, H3. But W2 will have to go in the middle. And in that case, this couple is sitting in the same column, which is not allowed, right? So this case will have 0 possibilities. Similarly, if we have W2 sitting here, again by the same logic, that means the same couple can never sit in the same row. So that next to each other was irrelevant. Basically, the question just had that the couple cannot sit in the same row. Even if they are not sitting next to each other, it's not possible that the other couple is not in the same column. Is that clear to everyone? Yes? Yeah. Let's see just for a second what we're missing. All men in same row. Yeah. In this case, we have 2 men and 1 woman in the same row. But which one woman is sitting with the other 2 men? We have to select that woman as well, right? Which couple are we which woman are we taking and making her sit with 2 men in the same row, right? So in addition, we will have to select which couple this woman belongs to. So that means this is 3 is equal to 72, and now 72 plus 24, that is 96. Okay, complicated, yes, but this is how we have to consider it case by case, making sure that we're not missing any case. Okay, another 4 married couples that we have to arrange. They are sitting in a merry-go-round with identical seats such that men and women occupy alternate seats. Okay, so there's a merry-go-round with 4 married couples, so 8 seats. So we have 8 seats, 8 identical seats. That means these seats are not numbered. We are not saying that one has to sit here to one seat is different, second seat is different. They are just 8 identical seats, so circular arrangement, right? Now, what is the condition? The condition is that men and women occupy alternate seats, okay? And no husband is seated next to his wife. Strike one. $57 is the answer. 57. No. Is it 96? I don't think it's 96. Let me check. 96 is not the correct answer. The answer there is wrong. The answer there actually hasn't been changed since the previous slide. So let's solve it. But I know what the answer is. Yes, 12. 12 is the correct answer. Let's see how. It's very easy. Just you have to think very logically. Okay. So let us, because they are identical seats, we will follow the circular arrangement problem. How did we do that? We fixed one person and then we arranged everyone else around that person, right? N minus 1 factorial. So let's first arrange the men. So let's say we have husband 1 sitting here, because it's identical, it doesn't matter. So we fix the seat of first husband. Now one husband goes here, one here and one here, because they have to sit on alternate seats, right? Now we have to arrange these 3, so 3 factorial. Now let's say this is our arrangement. We name these as husband 2, husband 3, husband 4. Now we have, what are the options here? W3 or W4, because wife 1 and wife 2 cannot be here. Similarly, wife 1 or wife 4, wife 1, wife 2 and W2, W3. Now, as soon as we fix any one of them, let's say I picked W3 to sit here, then W3 cannot sit here because she's already sitting there, so W2 will have to occupy this seat. W2 has occupied this seat, which means W1 has to occupy this seat, and W1 cannot sit here, so W4 occupies this seat. So as soon as I fix one of them, all of the others are fixed. Similarly, if I fix W4 here, then W1 will have to go here, W2 will have to go here, and W3 will have to go here. So I have 2 possibilities for this, and as soon as I fix the woman to sit here, then the others are fixed. So 3 factorial into 2, which is 6 into 2, 12. Alright. So this is how you're supposed to arrange these in a circular arrangement. Find the number of maps F from the set 1, 2, 3, and the possible values are 1, 2, 3, 4, 5, such that f of I is less than equal to f of j. This is a pretty standard problem. We'll look at it, how we can actually do it, but just try it once. So the condition is that f I is less than equal to f of j for every I less than j. That means if 1 is less than 2, then f of 1 will be less than or equal to f of 2. F of 2 cannot be smaller than f of 1. Easy, yes. Let's see how we actually do this one, okay? Because I don't think we solved it in our theory session. So let's just look at one of the examples here so that you can handle any such problem in your exam. So f of 1, let's say f of 1 is A, f of 2 is B, f of 3 is C. So what's the condition? A is less than equal to B, less than equal to C, right? That is our condition. Now, and the values A, B and C can take are from here, which means if I have fixed B, if I know what B is, then what are the options for C? C can be B, B plus 1 and so on up to 5, right? And if I have fixed A, then B can be just like this. B can be A plus 1 up to 5. So we have to just count the number of possibilities for each of them. So if we have fixed A, then B can be 1 or 2 or 3 up to 5, right? And C can be 1, 2, 3 up to 5. Then again 2, 3 up to 5. So when B is 1, the possibilities for C is 6 minus B. B to 5, that is 6 minus B. So 6 minus 1, 5, 4, 3, like this, 1. So once we have fixed A as 1, then it can go from 1 to 5. If we had fixed A as 2, then we would have 2, and then here we have 4 options, 3, 2 options. So like this we have 1 option. So basically what we are doing is we have how many options for C? 6 minus B, and B can go from A to A or just simply we are doing sigma I goes from 1 to 5 for this, right? 1 to 4 for this, 1 to 3 for this. So basically what we are doing is we are doing sigma I goes from 1 to R, right? And R can go from 1 to 5. This is the sum we are doing because we're taking the sum 5, 4, 3, 2, 1. That will be when R is 5. Then last one will be when A is 5. Then B and C have to be 5, and in that case we only have one option. So when R is 1, then I will go from 1 to 1, and that will be what we are adding. So this is what we are solving, and now it's just simple. So sigma R square plus sigma R, that comes out to be half into 55 plus 15. So 70 by 2, 35. Alright. So this is how you're supposed to actually, if we went totally logically 6 minus A, 6 minus B, then the calculations would have been a little complicated, and I could explain this conversion of sigma as in how we can convert 6 minus A to R, but directly, logically, it just makes sense, right? That this is the sum that we are trying to calculate. So let's just find the sum, and the final sum is 35. Now we have some problems related to coloring, right? So again, there is not anything that you should do separately. If you just understand these problems logically, make the cases one by one, making sure you're not missing any case, then definitely you can do it without learning any new theory. Let's see how. We have a convex hexagon, not necessarily regular, just a convex, something like this. They are colored red. Okay. Each of the diagonals of the hexagon is colored either red or blue. Diagonal means any line segment joining 2 points that are not adjacent vertices, right? So for example, this or this, these can be red or blue, right? So how many of these are there? 5 again. Sorry. How many will be there? Total we can select 6C2 line segments, right? 6C2 can join any two of these 6 points. Now we have already taken 6 sides, so the remaining diagonals will be 6 into 5 by 2 minus 6, 15 minus 6, that is 9. So there will be, 9 line segments like this. I'm not going to draw all 9 of them here because it will be very crowded and you will not be able to understand the figure, but you get which 9 diagonals we're talking about. So just join any two points that are not adjacent and you get one of these 9 diagonals. So these can be either red or blue. Now n is the number of colorings such that every triangle AI, AJ, AK, basically to tell that we have a unique triangle. This is, let's say, A1, A2, A3, A6. Like this we have 6 vertices, and now we are taking any of these triangles. And what do we want? We want that every such triangle will have at least one red side. Now, if our triangle has any one of these sides, then we have a triangle that has at least one red side, right? Because we are including one of these sides. Which cases have we not taken care of? The cases when our AIAJ-AK triangle has none of the sides, none of these 6 sides as one of its sides. So which will be those triangles? Either if we join this, this and this, or A1, A3, A5, right? So it will either be A2, A4, A6 or A1, A3, A5. All the rest will have adjacent sides, right? Will have at least one of these sides. Adjacent vertices, basically at least one of these sides. So the only 2 triangles now we haven't taken care of is these 2. And with these 2 we have 6 diagonals. So we have to find the number of colorings for these 6. The rest can be anything, right? So the new problem becomes that what will be the total possible number of colorings for these 6 sides or these 9 diagonals, because we have covered those 6 sides. We have colored those 6 sides. We have to color these 9 diagonals, and out of these 6 we have to put the constraint on. The other 3 can be anything, right? So now we have to check what are the possibilities for these 6. All the serious students, I know you're getting disturbed by all the other irrelevant messages in the chat, but it's okay. Just ignore them and focus on the question. And once you have the answer, just write it in the chat. I'll give you a few more seconds while I explain the question again. And if you're not able to solve, it's okay. It's not a trivial question. So we will go through the question, go through the solution together. Now, the question is that we have 6 sides, right? It's a hexagon, it's a convex hexagon, but what is the condition? That it's not necessarily regular. It's a random general hexagon. Now we have colored each side of this hexagon as red, right? Now we have to color the remaining 9 diagonals. How did we get the 9 number? Because in how many ways can we connect 2 of these 6 points? 62. Out of which we will also get A1, A2, A2, A3, and so on, right? So we will subtract 6 and the remaining 9, 15 minus 6, 9, that will be the number of diagonals that we have, and we have to color these. So total ways of coloring these 9 diagonals is 2 raised to power 9, right? Because they can be either red or blue. But now we have a condition that every triangle AIAJAK, you pick any 3 of these vertices and you will have a triangle, and now each of these triangles needs to have at least one red side. So if we are picking 2 adjacent vertices, then we have made sure that they have that triangle has at least one red side, right? The only 2 triangles that we have in which we do not have this condition met is A1, A2, A1, A3, A5 and A2, A4, A6, right? So we have to just check how can we make sure that they have at least one red side. The sum of squares of digits of 9 is 94. What is the n we are getting? 94 is the correct answer, yes. But what is n? Because we need sum of squares of digits of n. So yes, if you have got the square, 94 is the correct answer. The sum of squares of digits should be 94. Okay, chalo, let's see how do we actually do it. So this is actually a problem of inclusion exclusion, right? We have to see we have to have at least one red we have to have at least one red side in each of these triangles, right? So let's define the opposite of this. Let's define a set where A1, A3, A5 have all blue sides, and similarly B is our set where A2, A4, A6 have all blue sides. What do we need? We need to find number of elements in A union B, and we will subtract that from 2 raised to power 9, which is our total number of colorings, and this will be our final answer. So n of A will be, we color all these 3 blue and the rest can be anything. So 2 raised to power 6, we have fixed the color for A1, A3, A3, A5 and A1, A5. So 2 raised to power 6, that is 64. N of B will be the same, 2 raised to power 6, because now we have fixed the colors for A2, A4, A6, these 3 sides. The remaining can be anything. Of course, we have an overlap here, so we have to subtract N A intersection B and A intersection B. That is, these 3 are blue and these 3 are blue. Now we have fixed the colors for all 6 sides. Now the only option we have left is for the remaining 3 diagonals, because we in total have 9 diagonals. So we have fixed the color for 6. So 2 raised to power 3, that is 8. So N A union B will be 64 plus 64 minus 8, that is 120. Is that it? So our total answer will be 2 raised to power 9, that is 512 minus 120. And we get 392. Is that it? Four, 1, 2, 392. And let's see the sum of squares of this digits. If we got it right, 9 plus 81 plus 4, that is 94. Alright. So this is how we do it. Then we need at least one. So it's always better that you go through inclusion exclusion route, where you check none of them are red and you exclude all of those cases. Okay, so it's a complicated one. I hope you will go through this video, all of these questions again, all of these questions that I have picked for you. You should go through all of these again. Even if you're preparing just for JEE, even then I think these are very good questions. If you are able to solve these questions, if you have been able to understand all of these questions, then you will be able to do any of the hard problems definitely in JEE. Olympiad, yes, you can still get harder problems than this, but this will be a good start for your prep. This will make sure that you can do at least 80% of the combinatorics problems. Alright, so the answer is 94. Now, another coloring thing, I'll get aside so that you can read the entire question. Unconventional dies are to be designed such that the 6 faces are marked with numbers from 1 to 6, with now 1 and 2 are appearing on opposite faces. Okay, so 1 and 2 will appear on opposite faces. Further, each face is colored either red or yellow. So we have two options for each face, either red or yellow, but the condition is that opposite faces always have the same color. So that means the face containing 1 and the face containing 2, both of those faces will have the same color, either red or yellow, but they have to have the same color. Okay, now 2 dice are considered to have the same design if one of them can be rotated to obtain a dice, right? If you can rotate a dice and get the same configuration, that means they are identical, right? There is no difference. There is no top face and bottom face. So if you get the same configuration after rotating a die, then that is the same die essentially. Find the number of distinct dice that can be designed. So the only condition that we have is 1 and 2 need to be on the opposite sides, and the opposite faces have to have the same color, either red or yellow. Okay, 48 is the right answer. Very good. Let's see how we can actually approach this problem. So let's make a dice. So we have a cube like this, right? Now let's fix 1 and 2. Let's say 1 is on the left face and 2 has to be on the right face. We'll color them later, but let's first fix the numbers. Okay, so 1 and 2 are on the opposite sides. Let's now fix 3 here, right? No matter on which face 3 is out of these 4, we can find a configuration where 1 is on my left, 2 is on my right, and 3 is on the top. So let's fix this configuration now. Now it's like a circular arrangement, right? You can rotate this and get the same arrangement. So now we have to arrange the remaining 3 numbers on these 3 faces. So 3 factorial. And now we have numbered the dice. Right, now we have unique configuration for the numbers. Now comes the color part. 1 and 2 need to have the same color. 3 and whatever goes on the bottom face need to have the same color, and these 2 have to have the same color. Basically, we have to color these 3 sets of opposite faces. So 2 option for left and right, 2 option for top and bottom, and 2 option for front and back. And that is your final number of configurations. So first you fix the numbers here and then you color the dice. So this comes out to be 6 into 8, 48. Okay. So this is just like circular arrangement, even though it's a cube, but it's like if you fix 1 here and 2 here, then you can just rotate the dice to get the same arrangement. So it is like a circular arrangement. Okay. The answer is 48. N is a natural number. Consider non-negative integer valued functions, which means f on 1 to an n, right? Satisfying f of I is greater than or equal to f of j for I greater than j. And sigma I plus f of I for all I going from 1 to n is 2023. I think they picked the number because the year was 2023. So choose n such that sigma f of I is the least. We have to pick the n such that sigma f of I is the least. Now, how many such functions can exist? So first we have to find the value of n, and once we have n, we have to find f of I. It's a little tricky, so let's just dive into the solution, okay? Meanwhile, if you want to try, you can pause and keep trying and then check the solution. Yes, function is non-decreasing, yeah. So, it's a non-negative integer valued function. So, we can only have integers as the answer of f of I. Now, let's just first find the value of n. So, we have I is equal to 1 to n I plus sigma f of I going from 1 to n. This is 2023. This we know is n plus 1 by 2, which means sigma f of I going from 1 to n is 2023 minus n plus 1 by 2. Now we have to find a n such that this value is the least. This value is least, which means n into n plus 1 by 2 needs to be maximum, but at the same time this is non-negative. The answer cannot be negative, so the sum can also not be negative. So this has to be greater than or equal to 0. Right? So now we just find the answer, the maximum n, such that this is less than or equal to 2023. And we have done this question before, right? When we are trying to find the maximum n, you just check which n will give you which is the highest n for which this will satisfy, because this is an increasing function though. So you will keep getting a higher and higher answer. As soon as you get a value which is greater than 2023, you will stop there and choose the n before that. So we need the highest possible n for which this inequality holds. You can check, you can solve this. The highest n comes out to be 63. Okay. So this is how we first needed to choose the n such that sigma f of I is least. What is this value? 63 into 64. So 63 into 64 by 2, sigma f I is 2023 minus 63 into 64 by 2. So 63 into 32, and we subtract that. So 2023 minus 2016, and the answer is 7. Not the answer, but sigma f of I. Now we have the problem we actually need to solve. Now we need the function such that sigma f of I is 7. Sigma f of I is 7. And the answers can only be non-negative integer. F of I can only be non-negative integer. It cannot be more than, it cannot be negative. So now sigma f of I is 7. We need to partition this into integers such that the function, as someone said, is non-decreasing. It keeps either it stays the same or increases, right? So that means if we go in the reverse order, then the highest number can either be 7 or 6 or 5 up to 1, right? So the highest number when it's 7, then all the other will be 0. So that means this will give 1 possibility. If it is 6, then we have 1 remaining. So the next one has to be 1. After that, all of them are 0. So this will also give 1 option. Now if it's 5, then we have already taken 5 out of this sum. We have 2 remaining. Either we can do 2 or we can do 1, 1. So 2 options. Now if we have 4, then we have 3 remaining. Either we go 3 or 2, 1 or 1, 1, 1. So 3 possibilities. If we have 3, then we can do 3, 1, 2, 2 or 2, 1, 1 and then finally 1, 1, 1, 1. So like this, it has to be decreasing because we are checking in the reverse order and the remaining are 0. So 1, 2, 3, 4 possibilities. What's the total so far? 2 plus 2, 4 plus 3, 7 plus 4, 11. And we have reached 3 now. Now let's fix 2. Now either the next one can be 2 and the remaining are 1. 3 ones, right? 2 plus 2, 4 and 3 ones. Or it can be 1 and then the remaining are all 1. 4 ones, right? So 2 options for when we have 2. Correct, 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 correct. Are we missing anything? As I mentioned in the first class, we have to check in the reverse order, right? So the highest is 7, we get one option 6, then one option 5, then either we have the next one is 2 or 1, 1. Then 4, the next one cannot be 4, right? It cannot be 4, so it has to be 3 or 2 and then we have 6, so the remaining is 1, or we have 1 and then 5 plus 1 because it has to decrease. So we have 3 possibilities here. And now if we have the first one as 3, so the next one can be 3, and in that case we have 3 plus 3 6 plus 1 7, 3 plus 2 5 plus 2 7, or 3 plus 2 plus 1 plus 1, or 3 plus 4 1. Right, these are the only options. 2, 4. We're missing one here. Now, if we have 2 here, so 2 plus 2, 4. Now, what's remaining? 3. We can have another 2 here and then 1. Or we have 2, 2, 1, 1, 1, or 1, 1, 1, 1, 1. How many? 1, 2, 3, 4, 5. Yeah. Right? So, these are the 3 possibilities. And finally, the last possibility when the maximum is 1, so all the remaining are 1 and we get one option for this. So 1 plus 1 2 plus 2 4 plus 3 7 plus 4 11 plus 3 14 plus 1 15. So you have to be smart with these calculations. Of course, there are other methods to solve this, but I think this is the most trivial one. You just have to make sure that you're not missing any of them. If you just consider them case by case, then you will have all the possible arrangements such that it's in decreasing order. Okay, so always follow an order so that you don't miss any case. And now the last question for this session, and then I think you will have done enough practice that you can solve more problems very easily. You have done almost every type of problems in these 2 sessions and as well as the previous 10 theory sessions. So this is the last question. Let's do this one. Consider 5 points in the plane with no 3 of them collinear. It's kind of like our hexagon problem. We have to color the sides such that no 3 of them have a same color. So now let's just look at another coloring problem, because that happens, that shows up in our Olympiad paper very often, right? These coloring things, and you just have to go about it logically. There is no one right solution. So that is why I've added 2-3 problems in this set so that you can actually see how to approach such problems. Now, so we have 5 points such that no 3 of them are collinear, which means no 3 can be on the straight line. We have 5 points. Every pair of points among them is joined by a line. In how many ways can we color these lines? How many arrangements are there? 5, C, 2, right? Which is 10. So 10 will be these sides, and the other, 5 will be these sides, and the other 5 will be the diagonals, which will form like a star. And these are all our 10 line segments joining each of the 2 vertices, each vertex with every other vertex basically. What is the problem now? The problem is how many ways can we color these lines by red or blue? We have to color them again either red or blue such that no 3 of the points form a triangle with lines of the same color. We cannot have the same color. If we pick, let's say, this triangle, any triangle, if you take any triangle, then these 3 cannot be same color. And now you pick any triangle and all the 3 sides cannot be the same color. That has to be true for every triangle here. So how do we go about this? We do it case by case. So case 1, all sides, we have a pentagon, right, which has 5 sides and 5 diagonals. So let's say all sides are same color, either red or blue, but we have same color. Okay, so 1, 2, 3, 4, 5. Now we are trying to form a triangle. We are actually trying to form all the triangles as that no triangle has all the same color as their sides. Basically, if we pick this triangle, if we pick these 2 sides, then the third side cannot be red. So it has to be blue. And that has to be true for every diagonal, because every diagonal here is forming a triangle with 2 adjacent sides, right? You take any diagonal here and it is forming a triangle with 2 adjacent sides. Now we have colored 2 adjacent sides as the same color. Red in this case, it can also be blue, but the third one cannot be that same color. So it has to be the other color. So that is why these, once we fix the color of the 5 sides, the 5 diagonals will have the other color. And now I'll just make sure that any of the other triangles are not having the same color. No, all of them are such that the 3 sides cannot have the same color. So how many possibilities are here? We color all of them the same color. Which color? 2 options, and then we have 1 possible arrangement once we fix the color. So 2 here. Now let's move on to the other case. Case 2. Case 2 is, now we had 4 sides are same color. Now let's say 5 sides are same color. Now let's say 4 sides are same color. So let's say 4 sides have same color. I'm choosing red. It can also be blue. We will count that again. So if I fix, now watch carefully, okay? If we fix these 4 sides, now this diagonal has to be blue because we are considering this triangle, and similarly this triangle also has to be blue. This diagonal also has to be blue. But if that happens, then this triangle is all blue, which is not allowed. So that means we get 0 possible arrangements for this particular case. When we have one side as another color, then this triangle will always be of the same color if we are trying to make sure that these two triangles are not of the same color. So anyway, we cannot have this condition met in this case. Now let's move on to the next case where 3 consecutive sides have same color, or 3 sides have same color. Okay. So now case 3 is 3 sides have same color. Now there are 2 options for that. Either 3 consecutive sides have same color, or 2 consecutive and then 1 opposite, right? If we are choosing 3 sides with same color, it can be red or it can be blue, but these are the only possible arrangements, right? 2 consecutive or 3 consecutive. This has 3 consecutive or 2 consecutive and 1 opposite. Now 2 sides have same color. We will not have a case 4 that 2 sides have same color, because if 2 sides have same color, that means the other 3 have the same color, and we already considered that. If one side has same color, that means the other 4 have same color, so which we have already considered. So this is our last case which has 2 possibilities. Let's look at them one by one. In this case, this top triangle, this has to be blue, right? And now these 2 sides are already blue, so this has to be red. Okay, like that we will start coloring each diagonal. Now this will be blue, and this will be red, because these 2 are already blue, so this will be red. Now this last remaining diagonal, the one yellow one, if I make this blue, then this triangle in the middle will be blue, so it cannot be blue. If I make this red, then this triangle here will be red, which is again not allowed. So that means there is no possible configuration for coloring these such that our condition is met. So 0 again. Okay, so just watch very carefully. If you missed something, then go back to the video and you will see how we were coloring every diagonal and we could not find any color for this diagonal, which means 0 possibility. Now let's come here. Here, how do we color these? We have these 2 as red, so we start with blue here. Now these 2 are blue, so red here. These 2 are blue, so red here. Now these 2 are red, so blue here. These 2 are red, so blue here. And now we can see that every triangle has at least one different color and two same colors, right? So this is a valid arrangement. So and that is the only possible arrangement. As soon as we fixed which two consecutive sides have the same color and which has the different color, then we get exactly one arrangement. We did that one by one and there was not any other option for this, right? So 1 here. But now we have to find how many ways can we have this arrangement. So bache, as soon as we fix the opposite side's color, I picked this side and I know its color, which means I picked the side 5C1 and I picked the color 2C1. Now as soon as I have this, I know that the adjacent sides to that one will be the opposite color and the other two will be the same color. And once I have this arrangement, I saw that there's only one possible arrangement, one possible coloring for the diagonals. So like this, we will have our final arrangement. So basically what did we have to do? We just had to fix the opposite side, which side and which color, and as soon as we did that, we had the entire coloring. So this comes out to be 5 into 2 into 1, 10. So 10 from this case, right? I know it's a bit tricky. You might have to go back and think about this on your own. That will be the best thing to do. All right. Now, so that means case 1 had 2, case 2 had 0, case 3 had 10. So the final answer is 2 plus 10. Answer is 12. All right. So if you are taking something away from this entire course, this entire practice session and the course session, what you need to do is make sure that you're counting all the right cases. You're doing that in some particular order so that you're not missing any case, you're not repeating any case, and that is all what combinatorics is about. I have said this in almost every lecture. All you have to make sure is you're counting every case and be a little smart about it so that you don't have to actually list all the cases in every question, but in some questions you have to list all the cases. But be smart about how you're counting them so that you're not missing any of them, you're not repeating any of them. Chalo, let's end the session here. All the very best. Keep practicing and definitely revise everything we have gone through. Definitely revise every question we have solved, every theory we have done, and keep practicing. Your Olympiad, your any exam that you're targeting will be amazing. It will go great. Okay. Chalo. Bye.